Okay, everyone. So we're going to get started on another kind of applied topic here. And so this is part of a really big part of calculus, which is about approximating functions with simpler functions. So probably the first and the most important kind of approximation is linear approximation. Most important kind of approximation. And this is a really, like I said, a big topic. Eventually, when you do calculus 2, it'll lead to something called Taylor polynomials. Um, where linear approximation is using a linear function to um, get as close as you can to some function that we're interested in. Taylor polynomials takes that to the infinite degree, and it uses extremely high degree polynomials to reproduce other functions. But so we're starting here with this kind of in mind as the ultimate goal. Okay, so we're going to relate derivatives to this idea of linear approximation, and we're actually going to give a meaning to these dy and dx symbols that we've been using up to this point. Okay, so linear approximation. And the linear approximation is nothing more than just the tangent line. So the tangent line of a differentiable function is the best linear approximation. Is the best linear approximation of the function near that point. So let me illustrate that with one example here. So here is the graph of y equals sine of pi x. Okay, so whenever we do linear approximation, you always work with a sort of starting point where you know the exact value. So what I'm saying here is if I let x equal 1, that would be right here, x equals 1, we know exactly what y is, right? Y is going to be sine of pi times 1, which is sine of pi, which is 0, right? That's 0 exactly. Now, here's where we start to approximate. What if we take an x value that's a little bit larger? Say x equals 1.1. 1, 2, 3, 4, 5. So that would be right here. That it would be x equals 1.1 because that's 2. Okay, so I want to know what is the value of the function at x equals 1.1, which would be right there. So maybe you can see it already, but the key idea is that if we follow the tangent line, so here the tangent line, it should just touch the graph at that point and go straight down. The tangent line is pretty close to the actual function for a while, right? So as long as we don't go too far away, we could just follow the tangent line to 1.1, and that would be close to the true answer. So here's what we do. First, we're going to find the derivative. So we're starting with y equals sine of pi x, because what we need is we need an equation of that tangent line. So what's the first step? What's the derivative of y with respect to x? Okay, derivative of sine is cosine, and we're using the chain rule here, so the inside stays inside, and then we multiply by the derivative of the inside here, which gives us cosine of pi x times pi. So now what is the slope at the slope of the tangent at that point, x equals 1, because that's where it's touching, right? At x equals 1 is dy dx is cosine of pi times 1 times pi. Now what is cosine of pi? This is one that we should know exactly. Cosine of pi is -1. So it's negative pi, which is negative 3.1415926, etc. Okay, so what is the equation of that line then? Well, the equation of the tangent line. Let's see. We're going to use the best. Usually, the best form is this what they call the point slope form. The point who's they, the points what we call the point slope form, which is y minus y1 is m times x minus x1. And we know that here the slope is minus pi, and the point x1, y1 is, it's that point, right? So it's 1, 0. So what do we get? Let's just finish it over here. So we have y minus 0 is minus pi times, oops, no, that one's a variable. That first x is actually just a variable x minus 1. So minus x, minus pi x, let's say plus pi. Okay, so that's the equation of the tangent line. And so what we're going to be able to say here is that, here comes the approximation. The linear approximation is that sine of pi times 1.1, which is that green value there. So the coordinates of this point would be 1.1, oops, got confused there. It would be 1.1 comma sine of pi times 1.1. And we're going to figure out the coordinates of this black dot, which is the linear approximation, which is going to be 1.1 comma something else. But they're close to each other. So it's, all I need to do is put in 1.1 into the line plus pi. Now, as long as I have a calculator with pi in it, this is going to give me a very accurate answer. So minus pi times 1.1 plus pi gives me negative 0.31415 141,592. And actually, you'll notice that it's actually the same digits of pi. It's just with a decimal place shifted over. 141,592. Okay, so that's the approximation. Let me write that in here. Negative 0.31, yeah. Negative 0.314159. And we can go as far as we like there. Let's just stop at 6 digits. So what is the true value? Notice that the exact value would be, well, I can use my calculator for that. Sine of pi times 1.1 is negative 0.30901. Now let me add one more decimal point, 6 digits. So how well did we do here? Well, we got the first digit right, and the second digit is close, but it's already diverging in the second digit. So that's how it is with linear approximation. It's reasonably good approximation, but if the new x is too far away, it starts to be a worse and worse approximation. Okay, so that's the basic idea for linear approximation is we're using the tangent line and just following along the tangent line, and we assume that that stays pretty close to the function. Okay, so now let's make a formal definition here. So here's an example of a function. Whoops, I have my highlighter still. This is a function y equals f of x, and this is the tangent line. This function just represents sort of a function in general. So we're not going to bother with the a specific formula. It just stands for some function in general. And we're going to be considering a point, let's say here, which is, this is going to be my point A. So that means that this is the tangent line at x equals A. Okay. So if f is a differentiable function at x equals A, then the tangent line is L of x equals, so let's think here, it's the slope times x minus x1 plus y1. So this is the point slope form again. And I know the slope there, right? The slope here is, well, let me point at this point, right? The slope is the derivative there. It's going to be f prime of A. And now it's the point here is, this is the point A comma f of A. So that's my x1 is A, and my y1 is f of A. So this is the general form of the the tangent line. And furthermore, it's also what we call the linear approximation of f at, maybe we could add this at x equals A. So what we know is that f of x is approximately the same as L of x, which is, again, f prime of A, x minus A, plus f of A, for values of x that are close to A, right? We can see that these, you can see that the difference here is not very big. If you start to go too far away, now the difference is growing, right? So this, but near this point, they're very close. So let me do a different color there. So near x equals A, f of x is close to L of x. And you might ask, well, how close? You know, close enough? How do I know it's close enough? And those are all good questions, but we're not ready to answer them yet. Okay, so those are the definitions. Now we're going to do another example. So let f of x be x times 2 minus x. So that's actually the formula for that graph. And we know that f of 1.5, so we know the value of the function at 1.5. We're going to estimate two different nearby x values. So let's just redraw the picture briefly. So x times 2 minus x, so that's a parabola that passes through 2 points. Oops, let me try that again. It's an upside down parabola. Oh, I could do better than that. Okay. I didn't do that well, but there we go. So we know this is the point 2. At 1.5, I know that the height here is 0.75. And now I'm going to use the linear approximation, which is this straight line here. And I'm going to determine the function at two nearby points. So I'm going to use 1.48 and 1.52. So this, it's so close, it's a bit hard to indicate it. All right, let's do it. So what is the linear approximation? General formula is f prime of A, x minus A, plus f of A. Here, where f of x is x times 2 minus x, which makes f prime of x. How are we going to take the derivative of this? Well, one thing we could do is we could multiply out the brackets. Let's do that. So if we multiply out the brackets, I get 2x minus x squared. And the derivative of that will be 2 minus 2x. And A is 1.5, which makes f prime, the slope of that red line is 2 minus 2 times 1.5, which is 2 minus 3, negative 1. The slope is negative 1. And what is the y value? We already know that. It's 0.75, but let's do it again anyway. So that's 2. I'll use the original formula there. So that's 1.5 times 2 minus 1.5, which is, yeah, 0.75. So what am I getting here? I'm getting that the linear approximation is negative 1. So I'm going to here, right? This is what I'm using. I know this. I know this. So it's negative 1 times x minus 1.5 plus 0.75. So that means that the function at 1.52 is approximately the linear approximation at 1.52, which is that. And let's see what we get. So it's, what is that? That's the difference. This is the run, actually. If you think about it, this thing is the run if we're doing rise over run, and that's so the difference between the 2 points is 0.02. And then when I multiply that by the slope, so this is the run. When I multiply that by the slope, I get negative 0.02. So that's the rise. If I zoomed in on this picture, it would look like this. So I would have the let's see here. I would have the run. So I'm moving over here by 0.02, and I'm going down by negative 0.02, which gives me the slope of negative 1, which is what it should be. So that's the zoomed in picture here. Is, I don't know, which way should the arrow go? Okay, now I can finish this. So I'm going down from 0.75, and I get 0.73. Okay, so what did I found that this, whoops, trying to highlight it, but I scribbled on it. Let's see if I can fix that. Uh-oh, okay. Let's see. Maybe I can just erase it and draw it again. No, it was just lagging behind me. Computers are wonderful and terrible at the same time, right? Okay. It's catching up to me, that's the problem. Okay, I think I got it. 0.73. So what I've just found is that f of 1.52 is approximately 0.73. Now let's do the other side. F of 1.48 is L of 1.48. So now what's happening is I'm going the other way here. I'm going from here and I'm doing a triangle that goes the other way. So I'm doing a run of negative 0.02. So it's going to be the same rise going the other way. Okay, let's finish that. So plus 0. Whoops. plus 0.75. So let's see, so I get a run going the other way, negative 0.02. So now the rise is positive. So now it's up by a little bit, right? 0.77. So I've found did the same thing as last time. So that's the equivalent to that, or approximately. Should be approximately. Okay, now here comes a slightly new question for us. So are these values overestimates or underestimates? Are they too big or too small? Now notice that the the blue curve is curving away from the tangent line. Let me draw it in blue actually. The blue curve looks like that, and the tangent line is actually above it, right? So the tangent line approximations are going to be above or higher than the actual function values, right? So that's kind of just a conceptual picture here. That the red dots are too high. So both of these values are going to be overestimates. They're slightly too big, too high, too large. And another way to point this out is that when the function is curving down like that, that's called concave down. Concave is like a cup, right? And if it's concave down, it's like a cup that's upside down. And so whenever the function is concave down, the tangent line is going to be an overestimate. Okay, so we can actually formalize that a little bit. And I have to point this out. This is new. We're going to say something new here. When is a function concave down? It's concave down if the second derivative is negative. Okay, think about this for a second. So first derivative negative, when the first derivative is negative, it means the function is decreasing. When the second derivative is negative, it means the slope is decreasing. It means the slope is decreasing. So let me draw that here maybe. If I have a function that's curving down like that, what's happening to the slope? Right? The slope is getting more and more. F prime of x is getting more and more negative in this picture, which is the same thing as saying it's decreasing. So that means that the second derivative is negative. This is called concave down. Second derivative is negative. So if the second derivative at a is negative, then the function curves down from the tangent line. So then L of x is an underestimate, like that. If the first derivative is positive, if the second derivative is positive, then the function curves up from the tangent line. It's going like this. So the slope is getting steeper, right? Here it's negative, getting flat, getting positive. Now it's getting more positive. That's concave up. And in that case, the tangent line is underneath. So then L of x oh, I said under here. That must have been very confusing. L of x is over in this case, and here it's under. Sorry about that. All right. We're going to be using the second derivative quite a lot now and then in the rest of the course. This is our first chance to use it. Okay, so I think we just have one more. Okay, so we have a few examples. I think I'll stop there and we'll do the next examples in their own separate video. All right, I'll see you then.